Hello, and here I will give a short presentation for our mini project. And the data set we choose is adult data set. And in data set, we have many personal information such as a person's age, occupations, educations, etc. So the aim of this data set is to predict if a person's income is over 15,000 a year or under 15,000 a year. Um, so this is a classical binary classification problem. So we want to build a linear neural network to do this prediction. And in this data, we have non-categorical attributes like work class, educations, mental states, occupations, relationship, race, sex, and native countries. And we also have 5 numerical attributes like the age, capital gains, capital loss, and hours per week.
Regarding the data processing and splitting, we first had to encode some categorical variables using one-hot encoding or other tools. Then we plotted the correlation matrix to see potential relations between the different features. We did this just to get a first look at the data and see how it works and see if there are features that are associated with others. Then we did a simple train test split, an 80-20% split, where we end up with train, validation, and test set. Of course, the train and validation parts are both the 80% of the split. Regarding the training of the neural net, we first chose a really simple architecture with the one linear hidden layer, where we, of course, have the input layer, which is of size 93, because our feature vector is of size 93. Then we had one hidden layer of 6 neurons using an activation, a sigmoid activation function. We tried with 6, 12, 32 neurons in the first hidden layer, but it gives us more or less the same results. So we just used the 6 neurons for this one. And we thought that we might try other architectures. So for the results, we end up with an 83% accuracy with one epoch. But after taking a look at the normalized confusion matrix, we see that 92% of the elements of class 0 are correctly classified. But we misclassify half of the elements of class 1. Now, we tried on more epochs, 20, and we saw that there was a notable increase in accuracy, 80% in the class 1, but that's still not enough because we're still misclassifying 38%, and that's a lot. So we thought of the possibility of putting multiple hidden layers, and so we created another architecture and tried to compare it and the intricacies of that neural network and compare it with the first one, the simpler one we used first, to try and observe and analyze to see if we can change this outcome.
So here we design a deeper neural network with 4 linear hidden layers, and we also do the batch normalize and the dropout to avoid the overfitting problems, and we want to see if it can improve our accuracy and have a better result. So here is the train loss of our model, and we choose 3 different activation functions like the sigmoid ReLU and the liquid ReLUs. So for the simple architectures, we can see that all these 3 architecture functions performs very well. They converge to a same point. And for the deeper network, we found the ReLU and the liquid ReLUs performs better than the sigmoid. And we can see that the ReLU and Liqui-ReLU converges better. So we found the problem, and the question is that why ReLU and Liqui-ReLU can have a better result than sigmoid, and this is the topic we want to study, vanishing gradient.
After having a look at the evolution of the loss function, depending on the activation function used, either sigmoid ReLU or leaky ReLU, we decided to take a look at the evolution of the gradient flow, or take a look at the gradient flow for the network itself and see if there is any problem with the gradient. For the three different activation functions, there are basically no differences, and that doesn't amaze us because it's just one layer. So there had no problem of vanishing gradient. There's no way for vanishing gradient to happen here. So when we tried the same experiment on a deeper architecture, that is the second network we designed, we can see that the notable difference is in the sigmoid function, where the gradient is much lower once at the second layer, and then it evolves really, really slowly. Whereas for the ReLU and leaky ReLU, we can see that the gradient is gradually diminishing, so it's not as fast as the sigmoid function, and that's where we can clearly see that there is a problem of vanishing gradient when using the sigmoid, to the contrary of using ReLU and leaky ReLU. Although there is this performance regarding the gradient aspect, we did not see much evolution regarding the accuracy scores. So maybe we might take a deeper look into the data, see if we can use either oversampling or undersampling, because the class 0 is 2 or 3 times more than the first class, and that's what might be have taken a toll on the number of wrongly classified elements.
Let's move now to a mathematical explanation of the behavior of our network. So we have an input, which is a vector with a size of 93, and that's because we have 93 features, as explained before. In each hidden layer, we take the output of the previous hidden layer, multiply it by the weight, add the bias, and then apply the activation function. And for the output, we have 2 possible results. 1 if the person has a salary exceeding 50K, and 0 if not. So our main objective was actually to define an activation function that will make the network behave better, which means learning fast and avoiding vanishing gradient problem. So our first choice was the sigmoid function. So you should know that this function is actually one of the most popular when using neural networks. It is also very useful for classification because it squeezes all the values between 0 and 1. But the main problem with this function is actually the vanishing gradient problem. So let's take a look at the derivative function. So after computing it, we obtain this formula, and after plotting its graph, we can clearly notice that all the values are actually between 0 and 1/4. So its range is actually 0.25. So how does this affect our gradient when we have more than one layer? If we recall the structure of our neural network, each neuron is derived from the previous. So it is the previous activity multiplied by some weight and then fed through an activation function. The error box, J here, returns the aggregate error of our system. Then we perform the backpropagation to modify the weights through gradient descent, such as the output of J is minimized. To do this operation, we need to calculate the derivative to the weights, as you can see here. To calculate the derivative of the first weight, we use the chain rule to backpropagate and obtain this expression. So let's focus now on this individual derivative. Since the output is actually the activation function of the second layer, we are using the sigmoid as our activation function, then the derivative of the output is going to contain the derivative of the sigmoid function. So the resulting expression will be this one. And if we put all these elements together, we obtain this formula. So as you can see, assuming that the weights are initialized randomly using a Gaussian with mean 0 and standard deviation 1, the weights are also between -1 and 1. So we can see that we are actually multiplying values that are in range 0, 1/4. So this is why in our case, when we have 5 layers, the gradient becomes small very fast. And this is what leads to vanishing gradient problem.
So how to solve this problem now that you are pretty sure that the root cause is the nature of the sigmoid derivative? This is where the ReLU activation function comes into place. So what is even this ReLU anyway? Actually, it stands for rectified linear unit. It's a piecewise function that corresponds to 0 if x is negative and to x if x is positive or equal to 0. In other words, if the input is negative, the output is 0, and if the input is positive, it will act like the famous identity function. We easily compute its derivative that looks like a typical step function. The value of the derivative is 0 if x is negative and to 1 if x is positive. So we are now distinguishing these two values, these two cases. When the value of the derivative is 1, is the problem solved? I mean, we are not facing the bound issue anymore like the sigmoid case. Well, yes, but actually no, because depending on the values of the weight, we might still face a vanishing gradient problem, but it's just to a lower degree. Also, now there's a problem when we consider the other case when the value of the derivative is 0. Since it's a multiplication, we're multiplying by 0, so the ReLU function can die and block backpropagation event. And layer after layer, we can never recover from this because it will not modify the weights in any way. Since not only is the output for any negative input 0, but its derivative too. This can happen, not every time, and actually sometimes it's a good thing because we want to generate an interesting property that is sparsity, but that's another subject. To avoid this, there's a solution is to normalize the input between 0 or 1, or there's another solution, is to use the leaky ReLU. For a very small gradient epsilon, that will be the output if the input is negative. So with a negative input, the leaky ReLU will not die. The learning will continue even though it is small. So all in all, it is difficult to solve the vanishing gradient problem, but there are some solutions.
In a nutshell, after using a one-layer architecture, we had a pretty good accuracy score. But even with the deeper architecture, we didn't manage to budge the score even a little. And the difference, the huge number of misclassified elements of class 1 is still a big problem. So we might take a look at the data, see if there is anything wrong. And we stumbled during our research across this project, which is Project Petri Dish, a project led by Microsoft in the sphere of network architecture search, or NAS, where they try to automate creating a neural network architecture in 3 phases. The first phase, where they have either a parent network, which we have, either the first one or the second one, and in the second phase, they start assigning new layers depending on the type of problem. And those layers can go from convolution or bag of operations. So there's a really wide range of layers that we can add. And the third phase is the one where we have a lot of models and they take the best ones by running a bunch of experiments. So I think this is pretty interesting because if we manage to get over the problem that we have in our data and further optimize our neural network using this kind of techniques, we might end up with a really good accuracy score and understand really better why we can get better accuracies with a deeper network.